Welcome back, and now we can dive in to looking at operations with matrices. And when I use that language, I mean let's do like addition, subtraction, multiplication, division with two matrices. So let's start with the easy ones with addition and subtraction. So it is possible, but I want you to think about how you would do that. So in this first instance, we have a plus b. Okay, and the instructions are perform the operation if possible. So I want to take a, add it to b if possible. Okay, well, this is ranked or order two by two, not 2 by 3, and this one is 2 by 3. Okay, how can I add those? And I don't know if I know a good algorithm. It would be nice, like if we had, skipping ahead, so I'm going to leave that one for right now. B plus C, this is also 2 by 3, and if I want to add them, an easy way I could add them is just add the corresponding entries, and actually that's exactly how you end up doing it. So when we take B plus C, we would add the entries of B and C. So that's, let's see, 3 in the upper left, 0 plus 3 is 3, 1 plus 1 is 2, 0 plus 4 is 4, okay, and then I get 3 and 7, okay? And that would be the addition, okay? So when I add matrices and, well, then subsequently subtract them, okay, I have to make sure they have the same order. So, and in fact, a plus b, they are not the same order, so this one is not possible. Okay, now for c minus b, again, same sort of thing. I want to subtract the corresponding entries. Okay, so row 1, column 1, take those entries, etc., etc. So 2 minus 1, that's going to be 1. 3 minus 0 is 3. 1 minus 1 is 0. And then for the last row, I'll let you pause and try it out for yourself. Here we go. Okay, so c minus b is that. All right, and now we get to a plus I2. We don't remember what I2 is. Oh wait, I2, isn't that just the identity matrix of order 2 by 2? So 1, 0, 0, 1. And so then if I do that, it would just be 2 and 4, and then the other entries would stay the same. Okay. And then lastly, I want you to try a plus d. Pause the video, try it out, resume when you're ready to see the answer. And there you go. It's a matrix of all zeros, also known as the zero matrix. But what that means is just that A and D, these are what we call additive inverses. Additive inverses. That's a B. Inverses. Okay, meaning that when you add them, you get the additive identity, which is the zero matrix. Okay, but nevertheless, we see that addition and subtraction, for that matter, follow kind of what we would normally expect with real numbers. We just have to define it saying, okay, add or subtract corresponding entries. Consequently, because of that behavior with real numbers, we actually get the following properties that or for matrix addition that extend from real numbers, commutative. So if you have matrix A plus B, you can actually say that that is the same as B plus A. Okay, and I'm going to say this is also for addition. Subtraction obviously isn't commutative. Associative, if you have A plus B plus C and you add the first two first, that is the same as if you were to do A plus B plus C and add the second two first. Okay, additive inverse just means that if you have A plus the opposite of A, you get the zero value, or the zero matrix. And similarly, if you take a matrix and add the zero matrix, and when I say the zero matrix, that's just a matrix of all zeros, you get A. Okay, so addition and subtraction work nicely. Scalar multiplication is another nice idea, and what this is not multiplying two matrices yet. This is literally taking a matrix times a constant. Okay, so for example, if you have A, B, C, D here defined, what is 2A? Well, 2A is just going to be taking the matrix and multiplying it by 2, meaning that every single entry in A gets multiplied by 2. So 4 is the first column, -2, and 6 is the second column. Okay, negative 3b, I'll let you fill out that on your own right now. And there you go. C over 2 really just means 1/2 times c. Okay, we're hiding it on you. So then you just get 1, 3/2, 1/2, 2, 1, 3. Okay. And last one. Now this one, you could imagine you can distribute the 3 actually, but the bad thing is that we can't, if we look at the orders, right? C is a 2 by 3 and D is a 2 by 2. So this one is not possible. I mean, yeah, you can distribute the 3, but you can't go any further. Okay. So there we go. Okay. And consequently, because the scalar addition or scalar multiplication operates a lot like normal multiplication, we get a few properties. With distributivity, we can say if we have a constant times a matrix A plus B, you can distribute the constant, so it'd be CA plus CB. Okay. You could also view this distributed property in another way if you have the sum of two scalars and then multiply that to matrix A, you could distribute the matrix as well. CA plus DC, or DA rather. Okay. Associative, if you have, you know, C times D on all times A, you could do D times A first, and that would be the same as if you were to do CD, multiply those together first, and then multiply times A. That's okay. But bottom line here is that addition and subtraction, as well as scalar multiplication, works in similar ways to what we expect with real numbers. Okay, the only difference is that we have to have this, at least with addition and subtraction, we have to have the same order to our matrices in order to add or subtract them. Okay, and scalar multiplication is relatively straightforward. Just multiply everything by that given scalar. But is it possible to multiply matrices? Well, if you remember, it is, but we have to be careful. We'll talk about that in the next video.